And finally, we before reaching the conclusion, we want to show that here YI is the infection in city I, but we know that when you are faced with a pandemic, the city mayor may not have any idea about what could be the case. Like Wuhan could be the worst case, or could be in the relatively better case. So there could be uncertainties. So the model also takes care about uncertainty, and if the city mayor is risk averse, then the model can be modified to incorporate this risk averse decision maker. So we can introduce a concave function in order to incorporate that risk aversion. So after all these derivations, you can see we have like 4 or 5-page derivation about this social optimal optimization process. And through that process, originally think about if you have 360 cities, when you want to impose the route-specific restrictions of travel, then you have like 360 to the power of 2 type of parameters to manipulate, right? Because city I to j could be phi ij is a parameter, but city j to I will be phi ji. So you have so many parameters. But through our optimization process, we're able to down to push down the number of parameters to be estimated, gigantic number of parameters, to only have 2 times n minus 1. N is the number of cities. So that means that it makes the computation possible as a decision maker for the whole China, or each city's specific travel. What's the optimal restriction? We can measure that as a result of reducing the dimension of these parameters. And here, this is so far we talk about everything about the coordination, because if you look at this function form, this is a summation of infection from I, but all the I's. So as a social planner, you want to minimize the infection all over China. But if there's no coordination between cities, then it's in a different world. Each city will just try to minimize their own infection. And GI is the cost attached to each infection, and the cost is specifically public health cost. So in this world, without coordination, things will be different.